And Number Theory seminar again. So we are pleased to have our next speaker, Professor Jeremy Lovejoy from CNRS Paris. He'll be talking on Bailey pairs, radial limits of Q hypergeometric false data functions, and a conjecture of Hickam. Over to you, Jim.
Okay, so let me share my screen.
Yeah.
Okay, looks good, I hope.
Mm-hmm.
Let me close the, I don't want to see my face. Okay, I'm a bit riled up there because, yeah, like I said, the internet went down here just like 2 minutes before my talk was supposed to start. So I'm connected with a hotspot, and let's hope that holds up for the 50 minutes. Okay, so thanks to the organizers for the invitation. Thanks to everyone who is here to see the talk, and thanks to everyone who is watching the recorded version. So this is called Bailey pairs, radial limits of Q hypergeometric false data functions, and a conjecture of Hickam. So this is a report on my recent paper with Rishabh Sharma, which is to appear shortly in the Kyushu Journal of Mathematics. And the title is the same as the title of the talk. I'm using my cursor to point. If people can't see the cursor, let me know. Okay, so here's a brief outline of the talk. So often when we talk about Q-series and special functions and number theory, we talk about analytic functions inside the unit disk, so absolute value of Q less than 1. This talk is about a slightly different world, and this is the world of Q-series at roots of unity. So I'll start by talking about Hickami's results, which says that a certain Q hypergeometric false theta function has radial limits that are equal to a truncated version of that false theta function. So I'll say more about that. And then once I talk about Hickami's result, I'll talk about Hickami's conjecture, which is just a generalization of his result that he couldn't prove. And then I will talk about how to prove Hickami's conjecture using Bailey pairs and some simple ideas from Q-series. And once we see how to do Hickami's conjecture, we will see that we can do this for a lot of different kinds of Q hypergeometric false data functions. So I'll give some further examples and also talk about an application to identities of roots of unity. So these are Q-series identities which hold not inside the unit disk, but do hold at roots of unity. And then I'll conclude with some remarks. Okay, so this is the outline. So let me start with the Q multisum. So this is Hickami's result in the first part of this talk. So for m bigger than or equal to 2, let's define this function phi sub m tilde. So this is Hickami's notation. I'm just preserving that. So we have a Q hypergeometric multisum here. This is the kind of thing we're used to seeing. Looks like something you would see in the Andrews-Gordon identities or something like that. The product of Q binomial coefficients, some powers of Q. There's a sign here. Something you might not be used to seeing is this power of Q in front. From a number theoretic perspective, we'll see shortly that it's a natural thing to do. And just to know, on this other prefactor m, so this is just m, and Hickami put this m in for his own convenience, so I will preserve that throughout the talk. But it's not doing anything there, just sitting there. Okay, so here and throughout, I use the usual Q-series notation, which I don't think I have to explain to this audience. So in particular here, I have Q binomial coefficient. All right, so this is a Q hypergeometric multisum. It turns out this is a false data function. So what do I mean by that? So here's the identity. So phi sub m tilde of Q is equal to, well, here's this constant m again. So the sum chi sub 2m of n, Q to the n squared of 4m. And this is why we had this factor of Q out front. It all comes into this expression. So chi sub 2m of n is an odd periodic function defined in this way. So chi sub 2m of n is 1 if n is congruent to m minus 1 mod 2m, minus 1 if n is congruent to m plus 1 mod 2m, and 0 otherwise. So what I mean by a false theta function here is that this wants to be a false theta function, but this wants to be a theta function, but there's a problem with the signs. So it's not modular, and that's because this periodic function is odd. If it were an even periodic function, then we'd have something, a classical false theta function, which is modular. Or if we had a little factor of n in here, the odd periodic function, that would be a weight 3/2 classical theta function. But as it stands, this is a false data function. So these are not modular, which is something unfortunate, but one good thing about functions like this is they have well-defined values at roots of unity via radial limits. I'll say more on this later, but to describe Kami's results, I'll just leave it at that. So let zeta sub capital N be e to the 2 pi I over n. And so for these values at roots of unity via radial limits, in our case, we have for coprime integers m and n with capital N bigger than 0. So I'm abusing notation here twice, actually, because this limit should be a radial limit. And this is not really the value of the function at the root of unity, but we can think of it as the value of the function at the root of unity. So phi sub m tilde of zeta n to the m is equal to this limit. So this radial limit as q approaches this root of unity from inside the unit disk. And this is just the expression. Okay, so this is just classical stuff. This is asymptotic analysis of false theta functions, and they're just formulas for these radial limits. So we can, and I'll show how to compute these later. I'll say a little bit more about how to compute them later. But I'm just going to write it like this. So this is a bit abusive, but I'm going to say this is the value of the false theta function at the root of unity. But I really mean a radial limit. Okay, and then Hikami defined a truncated version of this Q hypergeometric series, phi sub m of Q. And by truncated, I just mean that he truncated the sum. So instead of summing over all n1 up to n m minus 1, we just sum for all of these less than or equal to capital N minus 1. And then here's this capital N in the notation. Okay, so this is just a truncated version. This is a polynomial because Q binomial coefficients are polynomials, Gaussian polynomials, as they're called. And what did Hikami prove? So this is his result. He proved for the positive integer capital N, one has this identity. So this is the Q hypergeometric false theta function evaluated at zeta sub capital N. In other words, take the radial limit. And this is equal to up to a power of this root of unity, just the truncated version evaluated at zeta sub n. Okay, so there's a priori no reason why this should be true, at least not that I could see or that he could see. But it is kind of nice. We want to evaluate this function at root of unity via radial limit. We just take the truncated version and evaluate it at the root of unity. Okay, so this is his theorem. So how did he prove this? Well, if you haven't read the paper by myself and Sharma, or you didn't read the abstract of the talk, you would never guess how he proved it. But I'll tell you, he proved it by computing the Kashayev invariant of the 2-2m torus links in two different ways. So I write that I kindly omit the details, kindly for myself, more than for you, because that way I don't have to write down things that I don't completely understand and try to explain them, given that I don't completely understand them. But you can imagine generally what's going on. So there's some topological objects, torus links. As usually done in topology, you look at invariants to try to distinguish them, something called the Kashayev invariant. It has a life of its own. It's an interesting object. People study them. There are ways to compute them. And it turns out if you compute the Kashayev invariant of these 2-2m torus links in two different ways, you do it one way, you get this expression for the radial limit that I put up before. And if you do it another way, you get this truncated Q hypergeometric series evaluated at the roots of unity. So if you want to look at those details, they're in Hikami's paper, which is called Quantum Invariant for Torus Link and Modular Forms. It's from 2004. Okay, so this is Hikami's results. He proved it using knot theory. And then he generalized it to a conjecture. So in the next couple of slides, I'm just going to generalize everything that I presented before. So here we still have m bigger than or equal to 2, but now we take a between 0 and m minus 2. And so we define another Q hypergeometric multisum. So this is phi sub m a superscript a of Q. And things just change a little bit. So the power of Q instead of m minus 1 squared is now m minus 1 minus a squared. Most of the sum is the same. And then there's just this weird, well, you might think it's weird, product of Q binomial coefficients with this delta function. So this is the usual delta function. This is 1 if I is equal to A and 0 otherwise. So all of these are just usual Q binomial coefficients, but in one case, except for A equals 0, you have n I plus 1 plus 1. Choose ni. Okay, so when A equals 0, this recovers the previous function, which I say there. Okay, so this is the generalized false data function. Well, it's a generalized Q hypergeometric series. Hikami showed that it's a false data function, did so in a very impressive way using Q difference equations, which is something I would never try, but he did it and it worked. And so this is the expression. So this Q hypergeometric multisum, so there's this M again, is equal to the sum, so a similar sum, chi sub 2m superscript a of n, q to the n squared over 4m. And here we just have a different odd periodic function. So this reduces when a equals 0 to the odd periodic function we had before. So this is 1 if n is congruent to m minus a minus 1 mod 2m minus 1 if n is congruent to m plus a plus 1 mod 2m and 0 otherwise. Okay, so again, it's a false data function. Okay, so then he computed the generalized radial limits. So once we have this expression in terms as character sum, we can compute the radial limits of roots of unity. So Hikami did this. So here's the formula. So again, I'm being abusive with notation here. It's not really the value, but it's a radial limit. And this is the expression. So it looks somewhat like the previous expression, a lot like the previous expression. The only difference is this character comes along. Sorry, I call it a character. I should say periodic function, not character. Okay, and then he also defined the truncated version. So it doesn't take much imagination to define the truncated version. You just truncate. So capital N minus 1 is the upper limit of the sum. And then he conjectured that we have a similar result. So if you take the radial limit as q approaches the root of unity zeta sub n of this function phi sub m superscript a, then up to a root of unity, we get we can find this by evaluating the truncated series at this root of unity zeta sub n. Okay, so this is his conjecture. So after he made his conjecture, he wrote the following. It is unclear, which I slightly paraphrase, it is unclear whether the series phi sub m capital N superscript a of zeta sub n for a not equal 0 represents a quantum invariant for any 3 manifold. So, what to do? So he seems to be saying for a equals 0, we can prove this using Kashayev invariance and knot theory. But for a not equal to 0, he doesn't know how to relate this to any quantum invariance. So is the idea to define some generalization of the Kashayev invariant for a and m, which would then apply to these torus links, or to define some generalization of the torus links, for which the Kashayev invariant captures the case a comma m. So where does one go from here? And the idea we had was to actually just ignore all of the topology and just try Q-series methods. So this turns out to work, and it turns out to actually be really easy. And that's what I'd like to explain. Just for my own peace of mind, is everyone still there? My connection didn't cut out or anything?
Yeah, you're fine.
Okay, thank you. Okay, so here's how we're going to look at this. So we forget all this topology, and we just ask ourselves, so there's this truncated Q series, which looks like something we could deal with probably. Can we construct the series phi sub mn superscript a of q using Q-series methods? Right, and if we can construct it, can we prove an identity involving this series? And if we can prove an identity, can we identify the other side of this identity with the expression for the radial limits? Okay, so maybe this would work. Maybe we can just construct this series, prove an identity. Once we can construct this Q series, we have Q series methods. We can prove an identity or lots of identities. And maybe one of these identities gives us this expression for the radial limits on the other side. And so the answer is yes, yes, and yes, or the answers are yes, yes, and yes. This all works. And basically, the most obvious thing you try works, which is to construct this series using Bailey pairs. So let me talk about that. And when you construct this series using Bailey pairs, you naturally get an identity. And the identity that you naturally just get just gives you the answer you want. So let me show you how that works. Well, first, Hikami's conjecture is true. And moreover, it holds for any root of unity. So Hikami just made the conjecture for zeta sub n, e to the 2 pi I over n, which is natural in his world because in the world of quantum invariance, people really care about what happens at those roots of unity. But it happens to be true for any root of unity. So let zeta sub n superscript m be a primitive nth root of unity with n bigger than 0. This is the theorem. Then for any m bigger than or equal to 2 and 0 less than or equal to a less than or equal to m minus 2, we have this identity. So as Hikami conjectured, the radial limit here is obtained essentially by evaluating the truncated series. And again, apart from passing through either topology as Hikami did or passing through Bailey pairs, as we're going to do, it's not clear to me why something like this should be true. Okay, so I'm into the third part of the talk. We'll be going a bit faster than I expected to go, so try to slow down a little bit. A quick review of Bailey pairs. So I think a lot of people have seen these. So a pair of sequences alpha n beta n for n bigger than or equal to 0 is called a Bailey pair relative to x. We're used to A here, but A was taken already by Hikami. So I'll just use x. If beta n is the sum from k equals 0 to n, alpha sub k divided by q sub n minus k, xq sub n plus k. And again, I use standard Q series notation. Okay, and here's this first stroke of good fortune, which is that there are some Bailey pairs known which look a lot like the series that Hikami was looking at. In particular, they have this product from I equals 1 to m minus 1, or m minus 2 if we just shift m, of these Q binomial coefficients where 1 just has a plus 1. Okay, so for m bigger than or equal to 1 and 0 less than or equal to a less than m minus 1, the sequences alpha n, beta n form a Bailey pair relative to q. So alpha n is all this, and beta n is this. So the little n is also nm here. And actually, I worked this out in a paper of mine. So I got lucky there that I had already seen these when I saw Hikami's conjecture. I had already seen Bailey pairs that kind of looked like the series he was looking at. Okay. So then let's take these Bailey pairs and use the Bailey lemma. So the Bailey lemma says that if alpha n beta n is a Bailey pair relative to x, then so is alpha n prime beta n prime. So alpha n prime is just this, and beta n prime is this. I'm not going to read them all out. But the point is, if you input a Bailey pair, you get a new Bailey pair. You get a family of them because you have choices for B and C here. Okay, and then if you have this and you put this back in the definition of a Bailey pair, then you get an identity between finite Q series. So let's do this. And this is what I call the key corollary. So I'm not putting in the Bailey pair yet. I'm just using the definition of a Bailey pair and the Bailey lemma. So if I take B and C and let them go to infinity, simplifying a bit, we get the following. So if alpha n beta n is a Bailey pair relative to Q, then we have this prefactor, q squared sub n minus 1 is equal to the sum k equals 0 to n minus 1, q to the 1 minus nk, minus 1 to the k, q to the k plus 1, choose 2 plus nk beta k. And we get the sum on the alpha side, which I won't read out. Okay, so how does this help? Well, let's just insert the previous Bailey pair. So remember, our goal is to construct this truncated Q series of Hikami. So if I insert the previous Bailey pair and change m to m minus 1, this is what I get. So the sum n equals from n1, m minus 1 up to capital N minus 1. So this is the expression. And here's the right-hand side. Okay, so this is just what you get when you plug in the Bailey pair. So this is not quite Hikami's finite truncated Q series, but I was a bit ambitious when I said we need to reconstruct his Q series. All we need to do is reconstruct his Q series at roots of unity. So note what happens here if I take Q to be a capital Nth root of unity, well, then Q to the capital N is just 1. So this part disappears. And if you're careful and you use a primitive capital Nth root of unity, this thing here cancels with this thing here. Okay, and then what you're left with is Hikami's series. And on the right-hand side, what happens? Well, 1 over Q sub capital N, when Q is a capital Nth root of unity, this is a 0 in the denominator. And so it turns out that this whole thing is of the form 0 over 0. Okay, and then we can differentiate. Okay, so this is what I've been saying. We're almost there. When Q is a primitive capital Nth root of unity, the left-hand side is precisely the series we wanted to construct. Okay, everything to the power of capital N just kind of disappears. The right-hand side is of the form 0 over 0, so we can just differentiate. Okay, so I'll omit some details here, but if we just differentiate this expression and simplify, then we obtain that for a primitive capital Nth root of unity, zeta n to the m, we have the following expression. So this is the truncated series, evaluated at zeta sub n to the m, and this is just what we get, the formula in terms of zeta n. And now all that's left to do is compare this to the formula for the expression of the original series at radial limits. Okay, so what we wanted was that this expression is equal to this right-hand side. This is the radial limit of the original multisum when Q tends to zeta n to the m. So these aren't quite the same, but this follows after a short calculation. Okay, so you can imagine if you look at this sum, k equals 0 to 2mn, you split it into two sums, k equals 0 to mn and k equals mn to 2mn. In the second sum, you do a shift. So this is also the second sum is also from k equals 0 to mn. Use properties of the character or of the periodic function here, and the k squares end up disappearing, and everything just falls out nicely. Okay, so this is the proof. So Hikami's conjecture is true. The radial limits are obtained just by evaluating the truncated version of the series. There's no reason to go through all of the Kashayev invariant and the knot theory, decomposing your knot and computing things in all sorts of different ways. All you need to do is use Bailey pairs. Okay, so that's about the first part of my talk. Any questions or comments at this point?
Yes, so you used the Bailey pair relative to Q, comma Q. Yes, that's what you said.
Yeah, well, in the paper I wrote Q, comma Q, but in the talk I just wrote Q.
Yeah, whatever. Sometimes there are contiguous results where instead of Q, comma Q, let's say you take 1, comma Q.
Mm-hmm.
You know what I mean? There are some.
Yes, of course, yeah.
Do you get a companion result in this case? If you do that, would that work?
So I can't tell you if it would work or not because we didn't look at it. And in the next part of my talk, I'm going to give a bunch of further examples, and all of them use Bailey pairs relative to Q.
Okay.
So I have to think about it because I don't remember all the details of the proof off the top of my head, unfortunately. But I think the fact that it was a Bailey pair relative to Q was important at some point.
Okay.
But you know, maybe it works for 1 as well.
Yeah.
Anything else? Other questions? Okay, so this is one point I want to make, is that wasn't so hard. Bailey pairs are very useful. If you're looking at something, if you're looking at some statement about Q series, Q hypergeometric series, even if it's talking about values at roots of unity, you can still use Q series methods and theory of Bailey pairs to get the results. Okay, and then it turns out, since that was so easy, we had to, well, we wanted to look at more. So turns out there are other similar results for other Q hypergeometric false data functions constructed using Bailey pairs. So I'll give just one example in detail, and then I'll summarize some of the others. Whether there's a general principle here or not, I'll leave it to you, if you're interested, to look at, to say if alpha n beta n is a Bailey pair, then you have that the radial limits of some false theta function are equal to the values of the truncated version, something like that. General principle I know is that it seems to work nicely in every case we looked at. But that's all I have to say about a general principle. And in fact, there are actually other conjectures like Hikami's out there. I think Rishab is starting to look at these, where people in topology or somewhere else run across these false data functions, and they want to evaluate the radial limits at roots of unity using a truncated series. And they have some other conjectures like this. Okay, so let me outline the steps. So we proceed as follows. So step one, we prove that some Q hypergeometric multisum is a false data function using Bailey pairs. Step two, we use classical formulas to find an expression for the limiting values at roots of unity. Right, as soon as we have a false data function, as I said, then we have these radial limits at roots of unity. These are given by classical formulas, which I'll put up shortly. Then we prove an identity for the truncated multisum, again using Bailey pairs. In fact, using the same Bailey pair we used in step one, just with a different application of the Bailey lemma. And then we compare the identity with the values at roots of unity that we obtained in two. Okay, and it's usually just a short calculation away to get the result. So let me show you how this works. So like I said, I'll give one example in detail. Here it is. So this is step one. So for m bigger than or equal to 2, so there's no a in all of this. Let's define this function, c sub m. Again, I use tilde, just following Hikami's notation. And following Hikami, I leave a constant out front. But you can not think too hard about that. So 2m minus 1 over 2 times some power of q times this multisum. Okay, so this looks pretty similar to Hikami's Q series that we saw at the beginning. There's just this minus Q sub n1 in the denominator. And because there's this minus Q sub n1 in the denominator, I'm going to restrict to odd roots of unity. Otherwise, we can run into trouble. When we look at the truncated version, try to evaluate this thing at an even root of unity, we run into poles. I'm just going to forget about that case and look at odd roots of unity only. Okay, so it's easy to prove that this is a false data function. I don't need anything fancy. I take this classical Bailey pair relative to Q. And when I say classical, I mean it's probably written down somewhere, and it can be obtained with an iteration of the unit Bailey pair, if you know what that means. So something pretty basic. Anyway, this is a Bailey pair relative to Q. And we use an application of the Bailey lemma, and we find that our function c sub m of Q is equal to this. So here, chi sub 4m minus 2 of k. Well, this is another aperiodic function. It has a definition. Whatever it is not terribly important. But in this case, it's 1 if k is congruent to 2m minus 3 mod 4m minus 2, and it's minus 1 if k is congruent to 2m plus 1 mod 4m minus 2. So this is a false state function. So it has limiting values at roots of unity. And here's how we compute these. So I'm probably telling you too much here, but this is fact. So let's see f of n function is modular. Then as t of then we have the expansion. So I'm getting a stable. Just checking that everyone's there.
Yeah, Jeremy, there seems to be internet problem. So perhaps you can switch off the video. Maybe that would